Okay, so I guess we can begin. It's a great pleasure to introduce Wenguang Zhai from the China. Forgetting the name of the university. It's the Chinese University for Mining. Is that what is your sorry? What is your university?
China University of Mining and Technology.
Oh yeah, so it's the China Institute of Mining and Technology. Is that right?
Doesn't matter, yeah.
Yeah, okay. From Beijing, so it's a great pleasure to hear Wenguang Zhai on a very exciting new development in continued fractions. So over to you, Wenguang.
Okay, thank you very much. So first, I'm honored for get this chance to give a talk in the seminar. So I thank Gaura. So the title.
Wenguang, sorry. Can you move your camera a little bit? We see only half of your face. That's better. Thank you.
Okay. So the title of my talk is Empty Algorithm and Continuous Fraction Formulas Involving Ratios of Gamma Functions. So now let's begin. So one of continuous fractions belongs to classic research areas of mathematics in many branches, especially number theory. It seems that the definition of continuous fractions were used already of the element that was 200 before Christ. More than 2,300 years ago. And intensive study of continuous fractions started since Wallis and Branca, also a long time ago. So in this area, so many big names made contributions. For example, Euler, Jacobi, Perron, Hermite, Gauss, Cauchy, Sturgeon, etc. Among them, Sturgeon first invented the next theory of the continuous fractions. So now the great Indian mathematician Ramanujan found quite a number of continuous fractions expansions for product and quotient of 2, 4, and 8 gamma functions. So among those formulas, 3 are fundamental. That were entries 34, 39, and 40. So in chapter 12 of this second notebook. So these formulas actually have a very close relation to half-geometric functions, and most other formulas can be derived from these 3. We know that Ramanujan didn't give proof for these 3 entries. He left no clues about how they discovered these elegant continuous fraction formulas. So that is very mysterious. So now we look at the entry 34. That is a very beautiful formula. So suppose X, M, and N are arbitrary complex numbers, and P is defined by this. So that is the ratio of gamma functions. Here, the numerator and the denominator are both a product of 4 gamma factors. So suppose X is complex with positive real parts, or assume that N is an odd integer or M is an even integer. So then we have this formula. So this one. This is the standard symbol of continuous fractions. So we will look at later. So this is entry 34. So this formula was stated by Ramanujan in his first letter to Hardy. That maybe that letter was written in 1914, maybe 100 years ago. And the first proof was provided by Crick. The second proof by Barron. And in 2014, Reuter, his student Bruce Bent, gave elementary proof by the theory of hypergeometric functions. Now we look at the entry 39. X, L, and N denote arbitrary complex numbers. Suppose the real part of X greater than 0 or either N or L is an odd integer. Then we have this. We let Q also is a radio of gamma functions with both numerator or denominator for 4 gamma functions. Then Q has this formula, can be written in this form. So this is also a very useful formula. So the first entry 40 is more complicated, so we don't state it here. So in this talk, we will explain an algorithm. So I call it MP algorithm. So by this algorithm, we can explore some continuous fraction expansion of some functions involving gamma functions. So actually, not only for gamma functions, so for arbitrary functions. So we can, by this algorithm, we can rediscover some of Ramanujan's continuous fraction expansions. So for ratios involving gamma functions, actually there is only one exception. But also we can find some new formulas. So now we introduce some notation. This psi L x denotes a monic polynomial of degree L in X. So we use this symbol. So for brevity, this notation here is the product O and F. So that means this is a product involving the function F. And you can see actually, so positive and minus here they are all together. There are 8 factors, but here there's O. It means that is only 4 F is included in this, and it means odd part, and here is E. So actually, the O and the E means the number of minor signs in these formulas. So more precisely, so they are of this form. So here, so this the product of involving F is this 4F. So the product of these 4. So we can see that the number of minus is E, the 1. So this means even part. So there's no minus here. The 2. Here 2. Here's 2. And this one is odd. So the number of minus is 1. This is 1, 1, and here is 3. So we use this notation. So for let X be the function, real or complex. So usually is a real function, but the definition actually can be generalized to complex functions. So which is defined on some at 0 to infinity. So we assume that there exists a fixed positive number nu and a constant phi. Phi is not 0, such that this limit holds. So from this limit, we can see the asymptotic behavior of Gx when x tends to infinity. So if this limit holds, we say that the function Gx is of order x to power minus mu. So when x tends to infinity, we denote this fact by this formula, the R. R means the abbreviation of RA width. Okay. So this is symbol we will often use later. So this one. Now we introduce the definition of continuous fractions. We suppose an and bn are two sequences of complex numbers. The generalized continuous fraction for this form. This is the standard writing. But for simplicity, we write it in this form. This is the standard writing. And then we write it in this form. So here's k from n, n is from 1 to infinity. And we define this as the limit of the nth approximate. So this is the nth. Here is k from 1 to n. So and the above form is a limit of this one. This is standard in the theory of continuous fractions. So we use this for this one. So A0 before this one, we write it in this form. So A0 before this, but here plus is here. And this part means this one. So for we use this symbol to figure space. So now we introduce two kinds of formulas. We use the definition here. That x in a free variable and AM, BM, CM, three sequences which are independent of x. And the continuous fraction of this form, we call it type 1 continuous fraction in x. So this form. And this one. So we call it a type 2 continuous fraction. And here's AM, and here is polynomial of degree 2. So actually, the type 1 and the type 2, so depends the degree of polynomial here. Here is a linear polynomial, so we call it type 1, and here is polynomial of degree 2, so we call it a type 2 continuous fraction. So now we look at the motivation of our study. So given a real number alpha, which is between 0 and 1, and the q is a fixed integer whose value equals to 2. So we say that a rational number, this one, is a best rational approximation to alpha of order q, if this is true. So which means that the difference between alpha and this number is the smallest one. of all these differences. Here, n and m are less than q. So this is the best rational approximation. So this definition is very important in many branches of mathematics, especially in number theory. So it has many applications. So for example, for the circle method in the electron number theory, and also the Minkowski theorem in the geometry of numbers. So this definition is very important. So the most important thing is how to find the best rational approximation of fixed order. Usually there are two ways. So one way is the enumeration method, because Q is fixed. So then for these rational numbers, they are finite. Then we can compute all the differences. Then we find the smallest one. And another one is to use the simple continuous fraction. So this is the best rational approximation to real numbers. So the question is, now we give some real function, and how to find a rational function approximation to this fx. So this is our question. So here we assume that the problem is we do this type when x tends to infinity. So we're similar to the above definition of best rational approximation to real number when we propose the following definition for the case of functions. We say the best rational function approximation. So our definition is as follows. Suppose f is a function such that this is true. So we know the symptotic behavior of fx when x tends to infinity. So here c is non-zero constant. Here v mu is a constant number, positive integer. So this can be removed. This can be removed. So for the fixed given positive k greater or equal to 1, we say that this is a rational function. So which is a ratio of two polynomials. So both of these two polynomials are the degree of them are at most k. So we see that this rational function is the best approximation to f in the following meaning. So the difference of f minus this one, the convergence rate of this function, so it is the maximum of all these. So here is the fx minus, so PR and over qs is so this one and this one are polynomials of degrees, so not exceeding k. So for all these rational functions, the convergence rate of the difference, so the maximum is this one. So we see this is the best rational function approximation to f. So we remark that for arbitrary function, we don't know actually this is we define this which is a completely analog of this definition. So for arbitrary f, we don't know is the best approximation exists or not, we don't know. And the best rational function approximation of f. So if this does exist, so maybe it is not unique, maybe so 1, 2, or 3. So which are all best approximation to f. So in the here, so in the right side of 4, there are many, so infinitely many polynomials. So we cannot run through all the rational functions, because in the case of best approximation to rational approximation to real number. So in the right side, there are only finitely many numbers, so we can run through all the we can compute all the differences to of alpha, and that's the rational number. So by enumeration method, but in the case of functions, we cannot do that because there are too many functions. So now what we do is we choose some special functions, some special rational functions. So our approach is here. We use the special type rational functions. So of this type. So by Euclidean algorithm, so we can write a rational function uniquely as this form. So this form. So this is a continuous fraction. So here we suppose that P and Q are polynomials, and the degree of P is less than Q. So then, so it can be written in this form, and it can be uniquely written in this form. So now when we search for the difference in 4, we use a rational function of this type. So here, AJ, this series are real numbers, and here BJ of X, so all of them are harmonic polynomials. So the Euclidean algorithm actually implies only the existence of AJ and BJ. So we don't know the exact form of AJ and BJ. So we have to use some algorithm to compute these AJ and BJ. Generally speaking, the algorithm is theoretically is easy, but how to compute or realize the algorithm is not so easy. So now the problem is how to determine the two frequencies, AJ and BJ. So we shall explain one algorithm. We call it the multi fraction algorithm. So for short, we use MT algorithm. So it means the multi fraction. So the following is outline of MT algorithm. So we first find A0 and B0, right? But how to find these two, we explain shortly later. Then under the choice of A0 and B0 of X, we find A1 and B1 of X. Then under all these choices, we find A2 and B2 of X. And then we repeat this procedure. So finally, we can determine all AJ and BJs. So this is only an outline of MT algorithm. So Now we explain it in detail. So now the problem is look for we call it the K fraction, MPK of X. So it is the continuous fraction form. Yeah, actually. Oh, give me this. So this is a continuous fraction. But here we change the symbol lambda g. Here is a actually in the above formula 5 is a0 and here is bj, but we use lambda g and phi g. So now we look at the first step. So how to determine the initial correction to MC0 of X? It is lambda 0 over this. So in this, we first find the asymptotic behavior of F when X to infinity. We suppose this is true. We suppose this is true. Usually, this is an easy thing in analysis. So here, lambda 0 is a non-zero constant, and kappa 0 is some positive integer. So if suppose this is true, so anyway we can do it in some way. So now we can find a polynomial. We call it here is phi 0 kappa 0 x. This is polynomial of in x of degree kappa 0, such that the convergence rate of this difference is the maximum of all this. So here, this polynomial runs through all monic polynomials of degree kappa 0. So among all this, so this one is best. So because this is a monic polynomial, so we suppose it is of this form. This form. So we see that here the leading coefficient is 1, and then this so mu 0, mu 1, and mu kappa 0 minus 1. So which are kappa 0 so unknown coefficient. So our problem is how to determine so all these unknown coefficients. So we first look at the usual approach. So we suppose this is true. This is true. So if we can expand the difference into series of this form, because our problem is to determine the asymptotic behavior when X tends to infinity. So we suppose the difference can be written a series of this form. So which is a series from n from kappa 0 plus 1 to infinity. And this is coefficient. So it is easily seen that for this power series, there are infinitely many n such that the coefficient is not 0. Because the difference for this difference fx so has nothing to do with the this unknown coefficient. So for this one, so when we expand it into power series, so it is from 1 to infinity, so no problem. So we see that infinitely many n such that this is true. Now we suppose n1, n2, and n kappa 0 the k smallest n's for which these are not zero. Now we can determine so our coefficient, unknown coefficient mu0, mu1, mu capital 0 minus 1 by the following equations. This one, n from n1 to n capital 0. So here there are capital 0 unknowns, and there are capital 0 equations. So we can determine this unknown coefficient. So then we actually can determine this polynomial. But this approach is so theoretically no problem, because so there are these equations, capital 0 equations imply so capital 0 unknowns, so no problem. But the approach is very complicated, but because there are two, especially when capital 0 is large, so there are too many equations, too many unknowns, so it is complicated. So now we introduce another approach. Some iterative approach. So we determine the unknowns one by one. So we first introduce this polynomial. It is monic polynomial, and plus this one mu x to power this power, and there is only one unknown coefficient here. Now we expand this difference into power series of this form, of the following form. So here the coefficient is called n1 to n mu. So also, so it is easily seen that there are infinitely many n such that this is not zero. And now we let n1, so it's the smallest n for which so this is not zero. And then we can find the coefficient mu by this equation, because now there is only one unknown, so we can determine it by this equation. So this is the first value. Now we do the second one. So we already determined this value. So we introduce another polynomial. This also a monic polynomial, and this one. Now this time this mu is the unknown, so the coefficient. Now we do the same thing. We expand this difference into series, power series of the following form. Do the same thing, and the coefficient we call it A2. Here A2 is from capital 0 plus 2 to infinity. Also there are infinitely many n such that this is not zero, and we find the smallest n, and we get some equation. From that equation we can determine the value of mu. We call it mu capital 0 minus 2. And then we do the same thing, so repeatedly. And finally we repeat the procedure capital 0 times, and each time we determine only one coefficient. So capital 0 times later we get all the unknown coefficients in the by 0 in this polynomial. Now we can determine this polynomial completely. So this is some iterative approach. Although it seems a little complicated, but each time we determine only one coefficient. So from another point, that is simple than the usual approach, because we can easily do this by the computer. Okay, now the second step, we want to find the first correction. We call it MC1X. So this is a symbol of continuous fraction. So now first we find the smallest positive integer Q1, and then another constant lambda 1 not 0, such that this is true. So we compare the convergence rate of these two. So here is lambda 0 over. So this is our first polynomial phi 0, and plus this one. We find a expression of this form such that this is true. The convergence rate of this part to less than this one. This is different. This is actually that is to find the asymptotic behavior of this function when x tends to infinity. This is a very simple thing. So now we can compute this easily, and then we can find another monic polynomial. We call it phi 1 x of degree capital 1, such that the difference of this, so convergence rate of this is the maximum of all these differences. So here in right hand side for this formula, the phi x capital 1 runs through all monic polynomials of degree capital 1. So we do this by using the iterative approach in the first step. Actually, that's the same thing. So because this is a polynomial of degree capital 1, so we compute it. So capital 1 times determine because it is a polynomial of monic polynomial. So there are capital 1 unknown coefficients in this polynomial. So we do as we did in the first step. So then we use the above procedure repeatedly. We can determine MC1X, MC2X, MC3, etc. So we can find a rational function of the form 5. So it is a form of continuous fraction form. So then we can find a good approximation to Fx. So this procedure is called MC algorithm. So we look at so actually the MC algorithm is some repeated procedure for finding corresponding polynomials. So they are so we go back to here. So this CK of x in this form there are k plus 1 different polynomials. So phi 1, phi 0 first in the beginning phi 0, then second one is phi 1, and finally the phi k. So when we find each polynomial in each step, so we use several repeated procedures. So the most important thing in the MC algorithm is the repeated use. Then each time when we use we determine only one coefficient. So this is the MC algorithm. Okay. Now, if we can determine MCK of X for any K, so we use this symbol. Then we actually get a continuous fraction expansion of Fx. So this is the way to how we get some continuous fraction formula of Fx. So we find some formula continuous fraction expansion of Fx, but we don't know Fx really has this form. So now, if we can prove that Fx really has this continuous fraction form, we get some theorem. So we discover the theorem, or rediscover, because probably somewhere already found that formula. So if otherwise, if we cannot prove that Fx has this form, then we can get some conjecture. So we can realize the MC algorithm by the mathematical software. So for example, Mathematica, MATLAB, etc. But it is so anyway. So the procedure is very complicated because we use the many iterative approach. So we have to use very fast computer to do this. So we give some remark. MC, if MC infinity of X is of type 1 continuous fraction, so we may try to find the type 2 continuous fraction of this form. Of this form. So if it is of type 2, then we can find a type 1 form. So anyway, so Fx maybe have a different continuous fraction formulas. So in one case it is type 1 form. In another, can be written in the type 2 form. So we see that in the above MC algorithm, the asymptotic behavior, so the convergent rate of Fx, it is plays important role in our algorithm. So actually, especially in each step, we determine MCK of X. So this in each step in the MC algorithm, we have to do this. We determine the asymptotic behavior of F. So, but for some functions, sometimes it is not so easy to determine the convergence rate. So in that case, so there are other approach to do this. For example, in 2010, so Motif established a very useful tool for measuring the convergence rate of functions. So which claims that the convergence rate of a function depends on the difference of this function. So the detail can be seen in the following lemma. So we call it a generalized Motif dilemma. If F has a limit to 0 when x tends to infinity. And there exists some positive number lambda greater than 1 such that this is true. This is true. And then we have this. We can determine the asymptotic behavior of f when x tends to infinity. So that means if for this f, so if it is a little difficult to find if asymptotic behavior when x to infinity, we can do this. If this is true, then this is true. And for difference, usually for the difference, it's easy to find asymptotic behavior. So actually, Motif Dilemma is a special form of the well-known Stott formula. The Stott formula is of this. We want to find the limit of this. If this is true, the above conditions, so fx, so they should limit force, and also this is true. Then we get this. So this is the well-known Stott lemma, so in analysis. So it is very important, especially when we do want to determine the exact form of some continuous fractions. We can compare. The hospital rule is a very important result to determine the Taylor formula, and then for power series. And Stott formula is important to determine the nth approximate, and then to get the continuous fraction. So now we look at the MC review the MC algorithm again. So in the above procedure, if we can expand the fx into a power series of 1 over x very easily. So it's not difficult to determine MTK of x. So as we did before, that is we repeated the procedure. And similarly, so if not so easy to determine the asymptotic behavior of fx when x tends to infinity, but it is easy to find the asymptotic behavior of this difference. Then we can use the Motif Dilemma. Then we can use the MC algorithm. Also, in these two cases, there are many functions. There are some other functions which you cannot easily use the above two approaches to determine the asymptotic behavior. For example, the ratios of gamma functions. Ramanujan studied many continuous fraction expansions of this kind. So we can, so for ratios of gamma functions, we can employ approach developed also by Motif to treat this kind of functions. So now we introduce, we look at Motif transformation we introduce, we call it the key fraction relative error sequence, EK of X, which is defined as follows. So Fx, so this part is in the expression of the above MCK, and we define some error term. So E0 in this expression, and usually for arbitrary K in this form. It is easy to determine. So we will move this part to the left side, and then we will take the log, and we get EK. Here, phi 0 is the first multipolynomial, which is of degree mu. So then we have the following lemma. We call it the motif transformation. With the above notation, for any k, we will get the convergence rate of this difference equals this constant plus the convergence rate of the sum of these two functions. And for this part, it's a line function of this, and here is a line function of this. So the convergence rate of this equals this one. So the problem is, so we want to find the convergence rates of the difference of these two functions, and now we only need to compute convergence rate of this part, and this one. So we know that MCK of X is a rational function. So here. So if this part is also a rational function, then it is easy to compute the sum of these two. So if f is give a remark here, if f is a product of several gamma functions, and then for this region, we can this can be written as some rational function by a suitable change variable of x. So then if this part after some change variable, so it can become a rational function. Then, so using this, we can accelerate our empty algorithm. So now we already know the empty algorithm in detail. So that is one approach to determine the continuous fraction, special continuous fraction, and how to determine the corresponding MCK fact to determine the polynomial fact key. And then we use our repeated approach, and in each step we use the iterative approach. So by this approach, we can get the continuous fraction formula of some special functions. Now we look at some special examples. So this is an analog of entry 34 of Ramanujan. So just now we already saw the entry 34 from Ramanujan. Now we call it, this is an analog of that. So we call it entry 34 star. So it is this is called P. This part is called P. So it is ratio of 4 gamma functions. So here the numerator and also the denominator both 4 gamma functions, and in each gamma function there are altogether 4 parameters to act alpha, beta, gamma. So all these are complex numbers, but in entry 34 of Ramanujan, there are 3. There are 3 parameters, but here there are 4. So X, alpha, beta, gamma. So for this we call it P, and some conditions. So X is complex with 0 positive part, positive 0 parts, and the following either one of beta, gamma, or alpha is even integer. So anyway, under these conditions, then the same thing, this expression, 1 minus p over 1 plus p, it can be written as a continuous fraction of this form. So here is linear polynomial, and also all this here is lambda, is a harmonic or linear polynomial. Then this is this group, so has it is a type 1 continuous fraction. Okay. So especially in this expression, when we take the gamma 0, gamma to be 0, then we can get the entry 34 of Ramanujan. So in this case, we see that this formula is a generalization of entry 34 of Ramanujan. But this is only a conjecture. We cannot prove it up to present. And now another one is entry 39. This is a generalization of entry 39. We call it 39 prime. Yeah. And also we can write this entry 39 from 1. So this it can be written in this form. This is also a continuous fraction of type 1. Okay, now let's look at the ratios of 3 gamma functions. So in the history, we know that in the history, many authors, including Euler, Gauss, Ramanujan. So many authors study the continuous fraction expansions of ratios involving gamma functions. So and all these ratios are of the following form. So ratio of this form, 2 gamma functions, and this one is 4 gamma functions, and also this form. So numerator, the denominator are also 8 gamma functions. So it seems that no one has studied ratios of this form. So 3 gamma factors. So now we can give some examples of this type. The theorem 1 is that we under these conditions, then this function can be written in this form. And theorem 2, under these conditions, and this person can be written in this form. This is the fraction of type 2, because here polynomial of degree 2. Yeah, all this. And all the corresponding coefficients can be determined by these formulas, because we cannot read it because they are too complicated. So the following theorem 3, T is defined in this form, and then this expression can be written in this form. Now, this is also a continuous fraction of type 2. Theorem 4, the at alpha, beta, the 3 parameters, and then this ratio can be written a continuous type 1 continuous fraction of this form. And now the theorem 4, the at alpha, beta, so parameters, and this condition we have this one. It can be written as a continuous fraction of this form. It is of type 1. So capital M, lambda M can be determined by these formulas. And from theorem 1, we get this formula, this one, corollary of this form. And the corollary 2, the coefficient and this person can be written in this form. So it can be compared with the similar formula of Bauer, theorem 2. So this formula was proved by Bauer many years ago, or 150 years ago. So just now we have looked at several prime theorems, and also some continuous fraction expressions which are generalizations of entry 34 and 39. And for entry generalizations of entry 39, we can prove that. So these two. But for entry 34 star, we cannot prove it. So that is a conjecture. But for this, so we can treat them as theorems. So how to prove all these results? We have to use the very well-known transformation called Bauer mirror transformation. So if this continuous fraction it has some transform, we get back to some sequence we call Rm. So if and only if this number, so phi m, is not 0 for any m greater than equal to 1. So if under this condition, then the following is true. So this continuous fraction can be written in another form, this form. So this is the well-known Bauer mirror transformation. So all these theorems can be proved by this transformation. So we don't go into details for the proof. So two remarks. So this transformation is well-known and important result in the theory of continuous fractions. And another, so actually, for when people use the the transformation to prove theorems about the continuous fractions, actually they choose Rm, the frequency Rm, such that the phi this frequency is a constant frequency. That means this V2 is always equals 1. But here in our proof, we choose some suitable non-linear to factor the frequency such that we can use this one. This V2 is always minus 1 equals to minus 1. So this is different parts from the previous proof. So now I think I have to stop here. Thank you very much for your listening.
Okay, thank you very much. Very nice and fascinating presentation. Any questions or comments? Questions and comments? So, Wenguang, I have a question. I mean, you have an algorithm to write it, but it seems like you don't need a proof. I mean, why do you need a proof that it is, at each step you are proving that the convergents are very close? Can't you just use that to prove the continued fraction?
So actually, by this approach, we so anyway, so the when we use the computer to realize the approach, so we can do only a few times because it is the approach actually is very complicated because we use too many iterative times approaches. So anyway, by this approach, we can get continuous fraction of some functions. But for many functions, it is difficult to get the rules of the coefficient because they are too complicated. So only some special forms. For example, just now I mentioned the ratio of 3 GAM functions, and for some special form of these functions, we can get the continuous fraction. Yeah, we can get the how to write out.
Yeah, I think we lost you. Okay, I wonder if I'm gone or. Okay, I think I lost him. Can somebody tell me, am I there or am I gone or is he gone?
Yeah, we can hear you.
Okay.
I think the internet connection is slow there,
Ah,
isn't it?
could be. I mean, he's in China. It should be faster than us. So we might have got lost a little bit. I can see his cursor moving. Yeah, are you back?
Hmm.
Hi, Wenguang, we lost you for a bit.
Mhm. Can you hear me?
Yeah, now I can hear you.
Uh-huh.
Okay, so all right, any other questions or comments?
The question of what?
Any further questions or comments? Okay, so anyway, so let's thank the speaker. If you can unmute yourself and